Amazing. Right. OK, mic's working now. Well, we've got a really busy room. It's really filled up since the last talk, and everyone's chatting. So you've all started to wake up now, which is great. OK, so thanks very much to our first speaker for setting us off for the day. We are now going on to our second speaker. You might have seen we had a little technical difficulty there, but that's now all sorted. So we're raring to go. Next, we have Hannah and Benj. Benj has been working as a data scientist in London for 9 years. Before joining Cleo in 2019, he worked on recommender systems and social media analysis tools. His PhD was on collective intelligence in bird flocks. Hannah is a data scientist at Cleo, where she develops machine learning models to build an accurate and complete understanding of users' financial lives. Before that, she worked in a variety of product teams at Bulb, a renewable energy company building natural language processing systems. Hopefully our next speakers will have less trouble speaking than I will. So Hannah and Benj.
Thank you. Thank you for coming to see our talk this morning. Thanks for coming down to Data Science Festival on a Saturday. We're going to talk about natural language models for understanding personal finance at Cleo. So first, I'm going to give an overview of what Cleo is and how we use data science there, especially machine learning. Then I'm going to talk about the use case of large language models in our chat feature. I'll hand over to Hannah, who's going to talk about large language models for enriching bank transactions. Then she'll tie things together with some learnings across both the chat and transaction enrichment. So, who is Cleo? Well, Cleo is a personal finance app. Cleo aims to be the trusted relationship that helps you progress towards better financial health. The mission of the company is to empower people to build a life beyond a paycheck. And the app is only available in the USA now, so our users are in the USA. And the way it works is people connect their bank accounts and credit cards to this app. It's able to read the data, and then they can interact with the data and get insights using a chat interface. So the data has to be well understood, and it has to be presented in an accessible and engaging way. And so once they do that, they can access some other features like setting a budget, getting a cash advance, or building credit score. So compared to the last talk was kind of about the broader sense of data science, this is going to focus much more on machine learning. So at Cleo, we have at least 10 machine learning models in production that are trained and maintained by 8 machine learning data scientists. And this is within a broader set of data roles that encompasses 36 people across the company. So I'm going to be talking today more about shipping machine learning models and using them to power product features, but we also have data roles in product analytics and data engineering and analytics engineering, that kind of thing. So some of the use cases of machine learning at Cleo are for credit risk profiling, for optimizing how we collect payments, for understanding the user's bank transactions, and for powering the chatbot. And it's those second two, the understanding the bank transactions and the chatbot, that we're going to be talking about today. So, Cleo's chat feature. What do users come to Cleo Chat to do? Well, they want to access insights about spending that are presented with humor, and that's what this GIF is showing. They also use chat to navigate to product features, kind of like a search engine of a menu bar. They'll type in the name of the feature, and they want to navigate there or to get a button that will enable them to perform some action. And they also want help to get help using Cleo, so it has a customer service function as well. So this is the important thing here is that people are typing in questions, and we need to understand those questions well in order to serve their needs in terms of personal finance. Now, the way we understood the questions that users type in for many years is with so we have been using machine learning for this, and our machine learning intent recognition sits in a decision tree with some pattern matching and some regular expressions. And so a user types something in, we check it against regular expressions, different patterns. And because we were already using some natural language processing, we were thinking about how we could use the latest advances in large language models to improve the accuracy of this process. So just a question for you all. How many of you have used ChatGPT or Claude or one of these large language models? Great. Wow. Yeah, a lot of people across the room is kind of what I expected. I'm not going to give a big introduction into them. And how many of you are looking at how you can use them to add value in your business or add value in the products that you're working on? Great. You're in the right talk. OK, so the question may have come up to you. Why don't we just sub in ChatGPT? That's the chatbot. People can ask questions. Would that work? Well, it would work for a small subset of the questions. It depends what users are asking. So there are some questions like, what crypto should I buy? Or that we just don't want to answer. We don't want to generate any answer for that. We're not there to give regulated financial advice. There are other questions like, transfer some money, where ChatGPT would be happy to oblige and say, yes, that's fine. It will be in your account in 5 days. And nothing would happen. And then there's a sort of middle ground where we could use generative models, but only with exactly the right information in the prompt. So questions that are very specific to Cleo's product, so about a refund policy. Without information on Cleo's refund policy, ChatGPT would hallucinate some refund policy that sounds sensible but doesn't actually match the facts. So a lot of product help questions fall into this area, or it could be that we need information that's specific to that user, so some facts about their spending. So someone's asking, how much did I spend at McDonald's last month? If we give a generative model the right numbers, it can craft the correct response there. And then there's the green area on the right, where people are asking generic questions, where one prompt could work across all of our users and answer these questions with a generative model. So first, I'm going to focus on this area of getting the right customer service information into the prompt of a generative model so that we can craft answers to the user's questions that have a conversational flow to them. And the challenge we face is there's a huge amount of information on how to solve problems within the Cleo app. People have to know, is my bank supported? I'm having trouble connecting my card, and all kinds of different, I think it was something like 400 paragraphs of information. So not huge. I think eventually maybe a large language model would just be able to take all of this in one prompt. But what we're using now is something called retrieval augmented generation, which is basically fetching some information that probably contains the answer to the user's question and putting it into the prompt, like a robot going through a library and getting some select pages from books and reading them first before outputting an answer. And I have to give credit to my colleague Adnan for devising and building this system for retrieval augmented generation, and in fact, the next one that you'll see in this section of the talk as well. So the way this works is we take our 400 paragraphs of FAQ information that I talked about, structure each one as a question-answer pair, so it has some commonalities then to the chat context, and put that into a text embedding, and actually we use the GPT embedding API for that. all of these are indexed for approximate nearest neighbor lookup in a vector index, which I can talk in a little bit of more detail about in a sec. And then at query time, the chat messages come in, and we take that last snippet of conversation, embed it using the same embedding API, find its nearest neighbors. I think I put top 10 nearest neighbors there, but that's a parameter that we can tune. Top 4 might be more appropriate. And that process of fetching the contextual information, Adnan has built as a microservice. So that is a standalone piece, and the backend can call that with the conversations, get back the relevant articles, and then execute a call to another OpenAI API, the GPT-4, in order to generate a response that makes sense. So another bit of detail here is about the vector index. There's been a huge growth in development of these. We use something called FICE, which works all right for this kind of small and fairly static set of documents, but it's definitely something to look into, what form of vector database or vector index you should use. So that gave you a flavor of how you can come up with a solution with generative models to one category of questions that users are typing into the chatbot. But how do we determine what category the question is? Well, we have to divide up this space of things that people are typing in with decision boundaries. This is a classification problem. It's called intent classification. So, as I said earlier, we have been using machine learning for intent classification for some years now, but we're looking at how we can use the natural language understanding capabilities of LLMs to choose the right response generation method. So this is like multiple choice among a bunch of classes that will generate responses. And one way to do this is to fine-tune a large language model as a classifier. So it's still a generative model, and it's outputting tokens, not like a traditional classification model. So how can we prevent it from generating out-of-range labels? Well, a trick here is rather than having a long label that's in a text form, like the human-readable version of the label, that's something where a generative model would be happy to invent a new one that was out of range. But by encoding the labels into integers and then limiting the output to one token and lowering the temperature, it keeps this output of the generative model within the range of the labels that was seen in the training set. So that's an important trick for getting it to work as a classifier. And here we also fine-tuned an OpenAI GPT-3 model, because this is something that, we like the integration with OpenAI that I was talking about earlier. And this task, even though it uses these very fancy models, it requires the same kind of labeled data that people will be used to for other classification tasks. You have to have some sense of what the true label is for each request. The difference is that now we can look back further in the conversation. The initial pass at this is just like last 5 minutes of chats, but we could put other stuff into the prompt, like the context of the user, some facts about their personal finance, their subscription status, that kind of thing. So this gives examples of 3 snippets of conversation on the left, and then on the right, the labels that will be output after we've de-encoded them from integers. So let's zoom out and look at what this whole system looks like for powering the chatbot. You take some user context, you take the recent chat messages and put them into the intent classifier, and this categorizes the message into one of the intents, and then each of those intents has its own response class, so we can use this. It makes the problem more modular, so we can have different strategies for different intents, some of them with generative models, some of them with hard-coded, pre-written replies by our brilliant team of writers, some of them with retrieval augmented generation, like I talked about. And then if there isn't high confidence in any of these intents, then we can fall back to a generative clarification mode where there's a prompt that will say, large language model, ask this user what they actually mean, clarify their question. So we're able to use large language models there as well. And so this has been amazingly fast at getting this out, fast delivery since the start of the year, where it was that decision tree that I showed you at the beginning. I think apart from the user context bit, this is actually the status at the moment, including some A/B tests that are running on retrieval-assisted generation and alternative versions of the intent classifier. So the team put GPT-4 into production in a narrow use case in the app within 10 days of it being released in the API. So this is the kind of speed that we're trying to move at. So that wraps up this section on chat. And now I'm going to hand over to Hannah to talk about transaction enrichment.
Cool, thanks. Yeah, so Benj covered who Cleo is and how we're using large language models in Cleo's chat. But I'm going to talk about large language models for transaction enrichment, which is basically the process of converting raw bank transaction data into actionable information for a variety of uses across Cleo. I'll start with how our transaction enrichment processes have evolved over the years, and then look at some of the opportunities and early challenges that we're facing employing large language models. We're using large language models for all sorts of things across Cleo, some of which Benj mentioned. We're also using them for lots of different areas of transaction enrichment, but today I'm just going to focus on merchant matching. So what is merchant matching? It is the task of classifying the merchant from a bank transaction, but bank transaction data is really messy. There's no standard format between how banks display the data, and it often includes lots of additional information like the place that the transaction took place, the date, which can come in many different formats, the payment providers, some account numbers, which are not real here. And yeah, so here are some examples of different purchases made at Champy's famous fried chicken, and it kind of shows how the actual merchant in them comes up in lots of different forms between the different transactions. So yeah, it's not an easy problem to solve, but it is a really important one. We use merchant data everywhere. Here are some of the examples where we use it. This is Cleo's app. We use it to generate insights and to drive engagement in the app with our users. We also use it to make suggestions and show them opportunities for how they can make savings with their purchases. And we use merchants for income detection and for bill detection in a user's transactions, which can help them set up a budget and kind of really keep on top of their finances. So these are some of how we use it for users. We also use merchants to feed into other ML models that we have as a feature. So yeah, this slide is really to highlight what makes large language models so powerful and how that's relevant specifically to the task of transaction enrichment. So the first one is that they are trained on huge amounts of data, which gives them domain knowledge and contextual understanding. So what I mean by this is that because they've been trained on so much data, they already know what Apple or Exxon actually mean in a financial context. They know what a bank transaction looks like. They know what the places are. And then the second point is that because they've been trained on so much data, they are much better at generalizing than like previous machine learning models that have come out. So they can capture linguistic patterns that can't be captured by like regexes. For example, like I said, they know what dates and places are, so they could kind of learn to extract them in a more general way instead of just specifically looking for regexes of things. And the third one is this idea of the kind of one-size-fits-more approach with large language models. Again, because they've been trained on so much data and are really good at generalizing, they can be used in lots of different domain areas in a company. And yeah, it's kind of, they're just really transferable. So you could pick one up, use it for a new use case with relatively low effort of implementing it. Especially compared to having to get annotations from somewhere or like specifically inspecting and building rules for things. So now I'm going to take a step back to when Cleo was small and look at the first merchant matching process that was built. So this was approached as a named entity recognition task where we wanted to extract the merchant from the transaction. What we had was a large system of regexes and rules that were put in place, and over time these were added to by lots of different teams and people to kind of build up this big flow diagram that you can see, which, yeah, can get quite confusing for someone who's new joining and wants to make improvements. So as Cleo scales, this solution doesn't. It's very sensitive to changes in the way that banks format the transactions, which we saw before, and the rules don't generalize to these new formats or to new merchants that are coming up. And it also needs to be maintained, which is like a time-consuming process and also gets increasingly more complex as the complexity of your system gets bigger. So we knew we needed to improve this, and machine learning models are a natural place to look to. They're more flexible than a rules-based system and can generalize to new data. So we kind of initially thought of approaching this as a multi-class classification problem because we have a big set of merchants in our merchants database and a raw transaction. So you take the raw transaction data in, you put it in like any kind of multi-class classifier and output a label and a probability associated with that label. But this is an extremely multi-class classification problem. We have 5 million merchants in our database at the moment. So as your feature space gets very large, this gets a very complex problem, and it can be really hard to distinguish between those classes when there are so many of them. This approach also has another downside that it requires retraining when a new merchant comes in, which, yeah, just takes up time and isn't great. So there have been huge advances happening in the generative language model space, which got us thinking about how we can solve existing problems that we have in new ways using large language models. So instead of treating this problem as a multi-class classification problem, we started thinking about whether we could turn it into a text generation task, which would make it a perfect fit for these generative language models that like huge advances are happening in. So this is like a very broad overview of what it looks like. You just have the raw transaction data, pass it to a generative language model, maybe it's fine-tuned, maybe out of the box, and then ask it to predict a merchant, and then match that to one of the merchants in our database. So this is quite a neat solution. It combines the string cleaning process that we saw before with the actual entity extraction and also with the matching to a merchant. So yeah, we were kind of thinking this could be the best of both because it doesn't only look for substrings in the regexes like the kind of initial older approach we saw, but it also generalizes to new classes, which is something that we wouldn't get with like a standard multi-class classification problem where the model already knows what the label set that it needs to predict is. But yeah, this isn't like a perfect solution. There's always some issues that come up. I'm going to discuss some of those later on. But one of them is that because it doesn't know the label set, we need a way to deal with these out-of-range labels. Benj has already spoken about one way that we can do this, and I'm going to go through a different example. So when it doesn't exactly match to a merchant in our database, what do we want to do about that? And then the second kind of issue that we've come across is that depending on your model choice, large language models can either be like very big, very high compute and memory resource requirements, very expensive. So there's lots of choices to consider there. But before we go into them, let's look at some results. So we've found that we have an 84% match to what our current matching system does. This isn't necessarily the aim of where we want to be. We want to be better than this system, but it's a good place to start because it's where we have a lot of evaluation and training data. So I'm going to talk through these examples. In the top three, you can kind of see how the large language model has actually learned that kind of string cleaning process. It's learned to extract out the merchant and like know if it's a web link, then just to get the merchant out. The fourth and fifth example show where the model has kind of almost got it. It's very close. If you just had a person looking at that label and didn't know what it already said, you might be like, yep, that looks fine. So it's very close. It's not really wrong, but it will come up as wrong when we look at our training data. And if it's not a merchant that's in the database, then we also won't be able to match this to anything and kind of make those comparisons between merchants of where a user's spending. So it's important to have that link through the transactions of the merchant as well. And in the last case, the prediction is just better than the label. And that's kind of just highlighting why we don't necessarily want to aim for what the current system is. It's just a good like benchmark to start with. But there's some data in there that can be wrong. Which, by the way, in the last example, probably happened from some sort of like regex match that was put in place in 2018. So that's kind of also why we want to make the system better. So yeah, now I'm going to talk about how we've approached dealing with the out-of-range generated labels, specifically for the case of merchant matching. So, like I said, 84% of them match exactly to a merchant that already exists in our database, which is great. We can just mark them. That's done. But there is this other case where it's like the close match that we saw before. So, for example, Gap US or Gap, and we want a way to match them to a merchant in our database. So what we're using here is similar to how Benj mentioned before with the process of embedding a string and then doing a approximate nearest neighbor lookup in a big set of a vector database to get the closest match. So that's the approach that we're using for dealing with out-of-range labels here. I've put some examples of the similarity scores that we're getting. So this is just, we've just used out-of-the-box GPT embedding API and the cosine similarity, which is the similarity scores that we can see there. So you can see like Gap US and Gap, very similar, that's great. Wheeling Food Mart, very similar, that's great. The other thing that we found by looking at these GPT embedding similarities across the database is that they're actually all quite similar. They're like 0.76 is quite a high like similarity score, which actually kind of makes sense if you think about the grand scheme of everything that anyone could send to the GPT embedding API. They're both US companies, they're both merchants, they're both relatively short strings, so they actually are quite similar. We haven't done this, but one thing we thought if we wanted to kind of differentiate more between the merchants in the embedding space is by fine-tuning our own embedding model. But yeah, for now we found this good enough, and we use GPT embeddings API because it's just quick to get off the ground with. So now I'm going to talk about what model we're using. We're currently using a model called T5, which stands for text-to-text transfer transformer. It was released by Google. And since then, lots of kind of like fine-tuning models on top of this T5 model have been released using chain of thought prompting and have better performance. So there's still lots of interesting things happening with this specific model and lots of interest in it, even though it is a slightly older one. The main things about this model is that it's a transformer-based architecture similar to all of the kind of newer large language models that are coming through. The fine-tuning approach that we can use is text-to-text, so it's kind of like a perfect fit for our use case of the bank transaction, the raw bank transaction, and the merchant. And it's relatively small compared to all of the other ones. The smallest checkpoint has 60 million parameters compared with 175 billion that's in GPT-3. So yeah, but why are these specific things important for our use case? The first one is that we have a really, we use this in transaction enrichment, and we need to enrich 8 million transactions a day. So if we use an API, that would become incredibly expensive. So it's just much cheaper for us to host our own model in this really high volume use case. And because it's a much smaller model, it's also faster to fine tune and has much faster inference. So yeah, GPT, depending on your prompt or tokening, but it can take a couple of seconds to get a response. And this one is 1/10 of a second. And because it's also hosted by us, it's then kind of in our control if there's other things that we wanted to do to scale up how quickly this happens. But another kind of important thing to note here is that this is just a language model that we've chosen to use right now. But a bigger part of this is just setting up our infrastructure to kind of support this and use this new way of approaching the classification problem. But once that's all in place, as newer and cheaper and faster language models come through that are better, we'll be able to move really quickly on kind of picking them up and putting them into production. Cool. So yeah, that was the transaction enrichment use case. And now I'm going to summarize some of the learnings from across the different domains into some key themes that will hopefully be helpful for anyone keen to try out using large language models in practice. So the first one is this kind of new way that we've approached some older classification problems that we've had with large language models. Yeah, either fine-tuning, but using them still in a generative way, which is where a lot of the power is with the kind of bigger models that are coming through at the moment. So Benj talked about one example with the FAQ answering, and I went through another one with the merchant matching. The other kind of part here is that in the merchant matching case, it was a classification problem, but it was also a string cleaning problem, and that's really general to any other data domains. If you just want to clean some strings, this would be a good way to do it. We also talked through some options for dealing with the out-of-range generated labels that you might have, which is a drawback to using a generative model, like prompt fine-tuning, toning down the temperature, label encoding, and similarity searching. But yeah, another important thing here is that you still need good quality data to evaluate these models. It's not it's not perfect. It's still kind of that traditional ML workflow of evaluating your data, looking at where it's not performing, thinking about the risks in those areas. So the second point is just some of the practical considerations. There are lots and lots to think about. So yeah, you should definitely take some time to think about what's important for your use case. I've listed some of them here, like the latency and memory requirements. Some models are much bigger than others. This can make them much slower to run. The volume of requests, if you're using an API, this can become very expensive. And also, yeah, it can become costly. Whether or not you want to fine-tune the large language model, depending on how specific your use case of your domain data is and how much of it you have, you may or may not want to fine-tune. For example, if you're fine-tuning an OpenAI model, it's more expensive to run a fine-tuned model. The type of task, different language models are fine-tuned on different tasks before they're released. So it might be like summarization or generative or question and answering. And then the kind of final one is the control of data privacy. So if you're using an API, then you have much less control over like how that data is used, or depending on the contract of that company, of course, you just need to make sure that you're aware of how they're treating your consumers' data. But like I said before, setting your problem up in a large language model way, just gives you options to move forwards if your priorities change or if new models come in. And then the third one is just that we've used this combination of like embedding tricks, kind of, with the embedding data, getting the nearest neighbor retrieval. It's really practical, and we've used it in different places, like mining much larger data sets than could fit into the prompt, and also dealing with the out-of-range labels in classification. Like Benj mentioned before, like this is a Google trend graph of vector databases. And since 2023, it's just like that shooting up. Everyone is releasing vector databases. Like Benj mentioned, we're using Feist, but we're kind of hitting the limits with that in terms of memory. And there are lots of like hosted vector databases that you can use. OpenAI is a good place to look for recommendations. They're kind of frequently updating that. But yeah, that was the final learning. I'm going to hand over to Benj to quickly talk about hiring.
Yeah, so come join us. We have these open roles across our data chapter. The data scientists are dealing with machine learning, like some of the things that you heard about today, similar roles to Hannah and I. Data engineers who are working on the platform and how we support machine learning and batch processing of data, and then product analysts who are doing exploratory analysis of data and analyzing A/B tests in order to drive better decisions within the business. And we've got a great office in Shoreditch, not very far from here. We offer hybrid working, so people who are close enough can come in for a couple of days a week, say. And yeah, if you're interested in these roles, scan this QR code, come and talk to Hannah and I after the talk. Thanks very much.
Brilliant. Thank you very much, Benj and Hannah. Right, perhaps we can maybe ask one or two questions. Would you be willing to take questions? Anybody have any questions here?
Yeah, thanks. You mentioned vector databases are quite popular nowadays. What's the advantage of using them?
So, as I understand it, a vector database, you'll be able to like load in and delete documents without having to take the index down. Whereas, so it handles that kind of blue-green deployment where you're adding or removing while you're adding or removing documents. And they also have their own. You would be able to update your vector database and get the latest version of the search algorithms that they're using.
Thanks.
Right, shall we have one more question, perhaps? Here?
Hello. I was wondering if you try to continue the pre-training of T5, by corrupting some tokens in order to have domain adaptation on your data set.
If we did fine-tuning
No,
on our data?
Continuing the pre-training.
No, we haven't experimented with that yet. We've just done the fine-tuning. So we've picked up the base model and then continued fine-tuning on top of that. But yeah.
The banks do the job of corrupting the data for us.
Right, we probably can have one more question if there's one here. There's one in the front. Sorry, who came first?
Just very briefly, could you elaborate on some of the challenges you encountered trying to fine-tune these models, the T5 example that you indicated?
Some of the challenges in fine-tuning that is that, it took a lot of time. So we're using the small checkpoint. I initially tried with a larger model, and it just took a really long time to fine-tune, and inference was like 10 times as big, which is why we've ended up using the smaller one. That was definitely one of the challenges. Another challenge with using an older model is that there can be like a performance trade-off. That's something that we'll look to compare in the future by comparing it against a newer model, like what is that? But given that for this specific use case, we're not generating like a particularly large prompt, there's kind of that trade-off in like what should hopefully be a simpler use case, which is why hopefully a simpler model is actually okay for it.
Right, again, thank you very much, Hannah and Benj. And can I say as well, great use of memes for your talk to communicate information.